In RAM array organization, the memory cells are arranged in a grid structure, with to 2 power n rows, each representing a word line, and to 2 power m columns, each representing a bit line. Each cell can store a bit, and the cells are accessed via row and column address decoders that select specific cells for reading or writing. The detailed breakdown of the construction and working is as follows. The structure of the RAM array consists of memory cells, word lines, bit lines, row address decoder, and column address decoder. In the memory cells, each cell in the array stores a bit of data. In SRAM, cells are typically constructed using a combination of 6 transistors, 60 SRAM, while DRAM cells use a transistor-capacitor pair. For word lines, which is for rows, there are 2 power n rows, each connected to a word line. When a word line is activated, it connects all cells in that row to their corresponding bit lines for read or write operations. For bit lines, which is for columns, there are 2 power m columns, each connected to a bit line. Bit lines transfer data from the memory cell to the sense amplifier for reading or vice versa for writing. The row address decoder circuit takes the row address and activates a specific word line, enabling access to the desired row. The column address decoder circuit takes the column address and connects the desired bit line to either the input circuit or the output circuit for data transfer. The working of the RAM array can be understood by considering the address decoding, cell access for read operation, and for write operation. In the address decoding, when a specific memory cell needs to be accessed, the row and column address are sent to the row and column decoders. The row decoder takes the n-bit row address and activates the corresponding word line, and simultaneously, the column decoder takes the bit column address and selects the appropriate bit line. In cell access for read operation, the activated word line connects all cells in that row to the bit lines. For DRAM, when the word line activates, the charge stored in the capacitor flows to the bit line, slightly altering its voltage. A sense amplifier detects this small change in voltage, amplifies it, and determines whether the bit is a 1 or 0. And for SRAM, when the word line activates, the latch within the memory cell, usually a 60 SRAM cell, drives the bit line to a high or low voltage, which is then read by the sense amplifier. In cell access for write operation, the bit line carries the data, either data 1 or data 0, that needs to be written. And when the word line is activated, the bit line voltage either charges or discharges the capacitor in a DRAM cell or changes the state of the latch in a SRAM cell, thus storing the desired value. The benefits and challenges of the array structure involves 1. Scalability, in which the array structure allows for easy scaling by increasing the number of rows and columns, enabling large memory densities. 2. Performance, in which the access speed depends on the design of the word line and bit line drivers, as well as the sensitivity of sense amplifiers. 3. Power consumption involving each row activation, which consumes power, especially in DRAM, where frequent refreshing is required. This array structure is fundamental in RAM design, as it enables dense data storage and fast access, making it the standard in modern SRAM and DRAM configurations. Let us discuss static memory, or SRAM, which is unique because it retains data indefinitely as long as there is a continuous power supply. Unlike DRAM, SRAM doesn't require periodic refreshing to keep data intact. This stability makes SRAM an excellent choice for applications where quick, reliable data access is essential and where refresh operations could interfere with performance. Let's look at some key characteristics of SRAM. First, because it doesn't require refresh circuitry, SRAM is efficient in terms of design and power for many applications. This design simplicity also contributes to SRAM's high speed, making it especially useful in cache memory within processors. Now, to understand SRAM better, we'll explore its circuit structure and operation. A basic SRAM cell typically uses a latched circuit, which inherently holds the data without the need for recharging or refreshing. This simple architecture makes SRAM reliable for fast read and write operations. In the subsequent slides, we'll dive deeper into the actual components and mechanisms within SRAM cells to see exactly how they function. A simple 1-bit SRAM cell make use of two cross-coupled inverters as shown in the diagrams here. The various configurations of the SRAM cell, each with its own unique characteristics, are explained as under. Diagram A depicts the symbolic representation of the two inverter latch circuit with access switches. This shows a symbolic view of the basic SRAM latch, represented by two cross-coupled inverters. These inverters form a stable latch, holding the data bit. The access switches connect or disconnect the latch to the bit lines, enabling read and write operations. Diagram B shows the generic circuit topology of the MOS SRAM cell. This is the generic structure for a MOS-based SRAM cell. This illustrates the cross-coupled inverters, which are directly linked to the bit lines through MOS access transistors. This topology allows efficient data storage and access. Diagram C shows a resistive load SRAM cell. In this design, resistive elements are used as loads for each inverter in the cell. Although simpler, resistive load SRAM cells consume more power than CMOS cells and can be slower, so they are less commonly used in modern designs. Diagram D depicts a depletion load NMOS-based SRAM cell. This configuration uses depletion mode NMOS transistors as load elements instead of resistors. The depletion mode loads improve the cell's performance by allowing better voltage levels in the latch, enhancing the speed and efficiency compared to resistive load cells. Diagram E shows the full CMOS-based SRAM cell. Finally, we have the full CMOS-based SRAM cell, which uses both PMOS-based and NMOS-based transistors. This is the most common and efficient design, combining high speed and low power consumption. CMOS-based technology is widely used in modern SRAM due to its stability, lower power usage, and scalability for high-density memory applications.